Hi everyone. So today I'm gonna talk about section 1.5 function and continuity in Math 180 business calculus. Um, so in this function, we're gonna talk about continuity of a function, which is one of the very important topics in Math 180s. Please focus on this. In front of me right now, you can see that we have a graph of the piecewise function px. This is same with the example in chapter in section 1.4 last time for the piecewise function. In here, you can see that the changing number between two pieces, two pieces of the function px is 150. So 150 is changing point. Changing point. Okay. Because why? Because you see that like both of the pieces of the function is have 150. So 150 is going to be a changing point. So look at the graph. You see that the first piece, the first part of the graph is come from 0 to 150 over here, and it is a line, but it's come up to almost to 3,200 something. Okay, but then after that, it jumped down, or it just using another function for that second part after 150. They use 20x minus 250, and in here you see that there is like a hole at the first at the value when x is 150 for the second part of the px. So you can see that the graph is breaking at x equal to 150. So I can say that this function is not continuous. It's breaking down. Okay. So that is something that you may know a little bit. Need to know a little bit before we move to definition of the continuous function. Okay, so let's move down here. And I'm going to say that continuous function is a function whose graph runs continuously from one point to another point without any break or jump. So go back to the figure. You see that I can say it is a break, and I can also is like a jump, like from like when I make it bigger here. When you see that from the first part, the graph comes up to here and it jumped down a little bit to move to the second part. So this also called jump and also called breakdown. That's fine. Okay. So let's come back with this. Here we go. So I have two other graph here, to say which one is continuous function. For the first figure in the left hand side here with the figure 2a, I noted that the graph just continuously run from from the left to the right with no break or jump, even though in here is there's like a corner, but it's still continuously moving, so you don't have to worry about this point. You can still say it is continuous function. Okay, and for the second part, you see that easily in here there is like a jumping from the left to the left part to the right part. Here at this point, I can right away say it is not continuous. At the second part here, there is a hole which is like a brick of a function. So I can also, this is not continuous at this point. So not continuous. And then here is not continuous. Maybe I'm gonna just write in a shortcut, right? However, maybe you're gonna say, is there any way I can still see if this function is continuous? If you just consider say, let me change color. If you just consider at 2 point between say between this point and this point, then this is a continuous part. Okay, and or you can consider from this point to the other one here. After that, I think it's still moving with no hole and no break, because it doesn't have anything else to say. But I'm gonna just say from this point to this point here is still continuous. But in generally, if I'm talking about this graph, in generally, I'm gonna say it is not continuous. Okay, so all right. Let's move out. Okay, now I'm gonna talk about how to determine the function continuity. If you don't have like a graph, how can you determine it? Okay, so you have to check 3 conditions. Okay, 3 conditions that you need to make sure in order to say the function is continuous. Okay. Okay, so the first condition is FA is defined. The second one is Fx, the limit of Fx from x, that x approach to A has to be accessed. And the last condition is the limits of the Fx when x approach to A will have to be equal to Fa. Okay. So Now let's do some example. This is example 1. I want to discuss continuity of the function at the point where x equals 2. So I also provide you the graph. You can see that easily. There is a like a hole here in the graph. I can right away say it is a hole here in the graph at x equal to 2. Right. So then I can right away say it is not continuous. Yeah, x equal to 2. Okay. This is just for the graph. How about if I say that I don't provide you the graph, how can you do that? Okay. So you're gonna check 3 conditions to handle this. Okay. So first thing I'm gonna check 3 conditions. Yeah. So say number 1, fa. What is a in here? A is 2. Okay. A in here is 2. Okay. So I'm gonna say f of 2. What is that equal to? F of 2, I'm gonna put 2 in the fx. So I have 2 squared minus 2 minus 2, and then I have 2 minus 2, which equal to something on the top, say 4 minus 2, so it's 0 over 0. This is undefined. Okay, and since it's undefined, then it does not exist. And I can even stop here at this condition and say this is this function is not continuous. Is not continuous. Not continuous at x equal to 2. Okay, you can stop here right away to make a conclusion. However, because I want to show you 3 conditions, so I'm gonna just keep moving to show you what about the second condition. So say number 2. Condition number 2, I'm gonna ask you about. I'm gonna talk about limits of fx when x go to a. What's a in here? 2, right? Okay. So I had to find the limit of fx when I approach to 2. You maybe gonna substitute the fx into and see. So x squared minus x minus 2 over x minus 2. Okay, and in this case, you remember in 1.4, when they try to find the limits of a finite number, right? You had to, and this is like a fraction, like rational function. You need to factor. You need to factor all top and bottom, and then try to cancel if there is common factor between top and bottom. So if you know how to do factor, for this case, let me see. The top is the top is having like a quadratic equation. So so you're gonna have a times c equal to -2, b equal to -1, two number multiplication equal to -2, addition equal to -1, should be -2 and 1. And remember that a in here equal to 1 is special case. And right away you can change this expression become x minus 2 times x plus 1 in factor. And now you can see that there is common factor between top and bottom, which is x minus 2, and you can just say goodbye with it. I forgot a small thing that I may need to add it, which is limit. All right. And now the limit change to be x plus 1 and x approach to 2. And now you can just direct substitute to get 2 plus 1 equal to 3. And I'm going to say, oh, the limit is x. Limit of x. Then x go to 2 is x. Okay. So the first condition is not satisfied. The second condition is satisfied. Okay. Now I'm gonna check the last one, the third one. What is the third condition? I need to check. I need to check if the limit of x of fx, limit of fx, when x go to 2, is that's gonna be equal to f of a, which is f of 2 here, right? So, and and seeing you see that the limit equal to 3, but the f of 2 is undefined, then you're gonna say, oh, not equal each other. So not satisfied. Okay, and you can, like, if you you want to make a decision for this problem, you're gonna say, oh, this function is not continuous. Do not, sorry, continuous. Continuous. Continuous at x equal to 2 because of two conditions. Because of the first and third condition. You can say that. Okay. So that is for problem A. And now let's move to problem B. In problem B, you can see that if you look at the graph, you can see that there's a hole here, right? And they're asking me at x equal to 2, so I can write what it says. Even though there is a value of fx at x equal to 2 is here. There's value at here, right? But since you see the graph, there's a hole and on the graph, and there's jumping, right? Jumping. So I can just say right away, not continue. Okay. And now if I want to try to use check three condition without using, we are looking at the graph. Okay. So the first one will say f of 2. What is that equal to? Since I'm gonna talk about f of 2, I'm gonna using the second part when x equal to 2, right? So I have equal to 1. Okay, because this is p square function. Oh, actually, this is not f. This is g, right? And second part, I'm gonna talk about g limit of g x when x go to 2. Okay, for the p square function, you cannot easily apply the function like the other like the other kind of function similar like example 1 here. It's not a piecewise function, so I can right away apply the function into the limit. But in here is a piecewise function. You should not apply the function of g in here, because why? Because you have two part here. Which one you wanna apply in? You don't know, right? So I would like to break it to be I would like to check it. I would like to using definition of the limit. So I would like to check the limit of gx when x go to 2 from the left hand side. Okay, and the limits of gx when x go to 2 from the right hand side. I'm gonna check if they are equal each other. Then I can say limits gx is axis. Okay. So now let me check. So for the limit of gx when x go to 2 from the left hand side, what does that mean? X is not at 2. Okay, x is smaller than 2. Okay, x is smaller than 2. It's from the left hand side. It's moved to the 2, close to and close to 2. Right. So I will apply this function, this part of the gx, because why? Because in this case, x is not equal to 2. It just go from the left to try to approach the 2. Okay, so I still can apply that one. That's one on here. So limit x squared minus x minus 2 over x minus 2 when x go to 2 from the negative, from the left hand side. And this one gonna be similar with the first part here, part A here, right? You gonna just have to factor the top and bottom in order to cancel some things. So I'm gonna change it to be 1 second. Okay. So I'm gonna change it to be the limit of x minus 2 times x plus 1 divided by x minus 2 for x go to 2 on the left hand side. And then you still gonna cancel this guy, and you will get same as above. So direction of 2 gonna be 2 plus 1 equal to 3. Okay, for the right hand side is go from the right to that hole, right? To try to approach to 2. And again, this is not equal to 2. This is just greater than 2 from the right hand side. It's go try to approach to 2. So again, it's not equal to 2. I still have to apply the first part of gx on this limit. So I gotta have limit of gx when x go of x squared minus x minus 2 over x minus 2 for the x go to 2 on the right hand side. And then it should also gonna be limits of x minus 2 times x plus 1 over x minus 2 again, and for x go to 2 from the right hand side. And again, you can still cancel common factor between top bottom to get x plus 1, and then you just direct substitute to get 3. 2 plus 1 is 3. So I see that limits of the of gx when x go to 2 from the left gonna be equal to the limits of the gx when x go to 2 from the right hand side and equal to 3. So I'm gonna just say it is the limits of gx equal to both inside, and it is axis equal to 3. It's axis. Okay, so that is the first and the second, but they are both work. Okay, they both work for this case. Okay, but why I still have why when I look at the graph, I still can make sure it is not continuous at x equal to 2, even though I have 2 first condition is satisfied. So I'm gonna move to number 3, the last condition, and see. So I'm gonna check. I'm gonna check if limit of gx when x go to 2 is that going to be equal with g of 2. All right, and you see that g of 2 is 1, but the limit is equal to 3, so they are not equal to each other. Not equal to each other. So you can say not satisfied, or I'm just gonna have the cross here, not satisfied. All right, and conclusion for this, I'm gonna say gx, g of x, and they're not continuous. I'm not sure if we use is not, there's not, but yeah, you should understand that they're not continuous. I'll say they're not continuously running, but running. run at x equal to 2. Okay. So because of the third condition. All right. So let's move to part C here. Still having the same, the first part going to be the same at A and B, but the second part of piece y function here equal to 3, okay? And what is that? The graph is look like smoothly when you see it, and I'm gonna say I'm pretty sure it's gonna be continuous. Okay, so now let's using three condition to check it. So check three condition. I have h x h of a in here is 2, right? Gonna be so at x equal to 2, 8x equal to 3, and I will have this is the first one, so define. Second one, I'm gonna find the limit of 8x when x go to 2, and again I have to check the first and the I have to check the limits of the hx when x go to 2 from the left hand side, if they are equal with the limits of 8x when x go to 2 from the right hand side. And according to problem B, I can say yes, they are equal each other, equal to 3. So I'm gonna say equal to 3 and exist. Okay, certified. And lastly, is number condition number 3. I'm gonna check if the limits of hx when x go to 2 equal to the h2. And yes, they are equal each other and equal to 3. So I'm gonna say it x continuous. Oh, I think it's continuous. Is continuous better. Okay. Yeah. It makes more sense. And x equal to 2. All right. So I have finished example 1 for you already. We talk about how to check 3 condition for 3 condition for determine if fx is continuous. You can also do example 2 here, but I don't provide. We don't move to example 2 here, but I don't provide you the figure. So just gonna check by 3 condition. So let's say check 3 condition now. You have the solution. Check 3 condition. Okay, so the first one. First one is f of what is a in here? F of 1. Okay, because a in here is equal to 1. Okay, f of 1 will be equal to what? Copy this down. This x become 1, or the x now become 1 because we have input is 1, so now is 1. Okay, so I'm gonna have this equal to what? 1 square is 1 minus 5 plus 4. Top has to be equal to 0. So and bottom equal to negative 3. And 0 divided by anything equal to 0. So, all right. So still it is defined because f of 1 equal to 0. It's still defined. Okay. And let's move to check condition number 2. Condition number 2, I still have to check the limits of fx when x go to 1. And I'm gonna have limits of x squared minus 5x plus 4 over x minus 4 and x equal to 1. Okay, so because this is not a piecewise function, I can right away substitute fx become the function that they give me, and right away using the using the method in limit to find the limit with the finite number. Okay, so remember that we always the first step for this, we always have to substitute direct substitute in to get the limit. So in here, when you direct substitute, it should be exactly the same as plug in 1 into the function. I have 1 square minus actually, you know what? I have 5 1 plus 4 over 1 minus 4, and I still gonna have equal 0. Okay, and it is as this. And lastly, condition number 3, I'm gonna say limits f(x) when x goes to 1 is that equal with f of 1, and yes, it equals each other and equal to 0. So I will say that since I satisfy 3 condition, then I'm gonna make decision as f of x is continuous at x equal to 1. Okay. There is example 3 here. You still have piecewise function, okay, but it's asking you for determine the continuity at x equal to 4, but remember that 4 is not at the changing point, okay, not at changing point. Okay, so I don't really have to worry about this kind. Usually this had to be continuous, but if you want to check it, okay. Now let's see where x equal to 4, at which case, at which part for fx you want to apply this x equal to 4. You have to know that x equal to 4 is greater than 0, right? Sin is greater than 0, so you don't you will right away just using only the second part of the fx. Okay, and it's, remember that it is strictly greater than 0. Okay, it's not at the changing point, so you just right away apply fx at the second part. So f of 4 gonna be equal to check three conditions, right? One is f of 4 gonna be 316 times 4 square minus 3. Gonna be this guy go away. 3 minus 3 is 0. Okay. And number second condition, I have limits of fx when x go to 4 will be equal to limits of 3/16 x squared minus 3 for x go to 4. Okay, remember that at 4 x is not at the changing point, so you just want to apply the fx for the second part in this case. So it's just gonna substitute directly. Gonna get 316 times 4 square minus 3, and you're still gonna get 0 again. Okay, this is exit. This is define and exist. Both of the first and the second one is satisfied. The last one you're gonna say, oh, the limit of the fx when x go to 4 equal to the f of 4 equal to 0, and you're gonna say, oh, seeing 3 of these condition satisfied and f of x is continuous at equal to 4. Okay. Now, column 4, part A. You see that we are checking at x equal to 4, and 4 is changing point. Okay, x equal to 4 is changing point. Changing point. So maybe the function is not continuous. Maybe. Okay, we have to check it. So let's say check condition number 1, f of 4. What is that equal to? Since f of 4, that means what? X equal to 4. And since x equal to 4, you have to check at the first part here, because x equal to 4 is inside of this interval. So you're gonna apply 4 into here. So I have 1/2 times 4 minus 3. And you have what? You have 4 divided by 2 is 2 minus 3 equal to -1. Okay, and this is defined. Second one, you're gonna check the limits of fx when x go to 4. Okay, and this is piecewise function, and also the x at x equal to 4 is changing point. Then you need to check left hand side and right hand side. When x go to 4 for the left hand side, you will have, since it's from the left hand side, which is less than 4, okay, and goes to approach to 4, then you will have to apply the first part. Okay, so you have limits of 1/2 x minus 3 for x go to 4 from the left hand side. Okay, and this is very important. Okay, so remember that if I talk about the left hand side, when x goes from the left hand side to the 4, then that means what? I mean is less than 4. Okay, less than 4, then you have to apply the first part. So this is equal to, direct substitute, you're gonna get 1/2 times 4 minus 3, and same at the first part gonna give me -1. Okay, What about the second one? Limit of fx when x go to 4 from the right hand side, you're gonna have limits of, now seen from the right hand side to the 4. That means what? That means x now is greater than 4. And what? And you cannot apply the first part for this case. You are using the second part, seen x is greater than 4. Seen x is go from the right hand side to 4. So now you have here as negative x plus 3. And when you direct substitute for x go to 4 from the right hand side, you're going to have negative 4. Yes, negative 4 plus 3. And it's going to be same thing. Okay, still negative 1. Wow, I didn't even check that. Did I make a mistake? Let me see. 2, 4. Yeah, everything's look good. Yep. Okay. So it's seen limits of fx when x go to 4 from the left hand side will be equal to limits of fx when x go to 4 from the right hand side and equal to negative 1. So I'm gonna say the limit of fx had to be equal to negative 1, and it is exists. Okay. So I finished 2 conditions. I had to move to the third one, and the third one wanna check if f of 4 equal with limits of fx when x go to 4. And yes, they are equal each other and equal to negative 1. So again, I still want to say fx is continuous at x equal to 4. Okay, so even though it is piecewise function, but and the point that we are checking is at the changing point, but still it may be continuous also. Okay, so point B here look like we still checking condition at x equal to 4. Okay, but two piece of this function doesn't include the value for x equal to 4. Okay, so I'm gonna check for the first one, f of 4. What is that equal to? You don't have any value for x equal to 4. So I'm gonna right away say they not exist. And I'm gonna stop here and make a conclusion that f of x is not continuous at x equal to 4. So far so good. So I will talk more about determinant of the illustrated function is continuous or discontinuous at the point x equal to a. So if the function is discontinuous, specify which of the 3 condition is the first to fail. Okay, so in the example 5 here, you can see that if I'm talking about f of a, is that defined for this case? A, x equals to A is here, and f of A is at this close point here, and there is value for that, so I say yes, it exists, right? F of A is like this, does exist. And for the second part, if you see the limit from the left is go to this value of y, of x here. From the right hand side is trying to approach to the other value up here. So you will say f limits of fx when x go to a do not exist. For the fa, I'm gonna say define better. Exit is okay, but I'm just gonna follow the three conditions. And the last one, you're gonna say they are not equal to each other, right? Fa not equal to the limit of fx when x equal to a, because fx the limit is do not exist, so then we cannot make it equal to each other. So so conclusion for that is not continuous because of two conditions here. So not continuous. Yeah, x equal to 4. Okay. And the last example here, you're gonna see that it's smoothly going from the left to the right with no hole, no nothing else. So I'm gonna just say continuous. Okay. So I just finished session 1.5 today. Please go to XYZ homework to do the AS assignment 1.5. It's due on it's due on Monday 15. Okay, so make sure doing that, and also try to work on homework for 1.5 on XYZ. If you have any question, go to my live class or office hours to question me anytime. I'd like to help you. Okay, I see you on 1.6 later.